Hi, this is Dr. S.P. Asa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration control, we are mainly discussing about the control techniques, in which you see we discussed the two main phases, one the passive vibration control, and in this module we are mainly discussing about the active vibration control. So, this is the last leg of our module, in which we are going to discuss about the electromagnetic dampers. So, we started this journey right from you see the basics of active vibration controls, in which we discussed that if we have the main components like the sensor, like the actuator, or along with you see if we are coupling these two devices with the automatic control feature, then we can you see generate the cancellation force or the force which can act against the vibrating forces, through which you see the excitations are being there in the systems. And again you see here it absolutely depending on the location, the kind of sensor, and you see here how the actuation forces can be generated. Sometimes we need to amplify the signals, because whatever the sensing the signals are there, that is not even sufficient to counter attack the excitation feature. Or sometimes we need to add some kind of you see the external sources, so that we can supply at least this much energy to cancel out that force. So, we found that this is one of the excellent part by doing you see the active vibration control, but at the same time you see it absolutely absolutely depending on that what exactly the location where we need to apply the control, what is the service condition, what exactly you see the operating features are there of the entire system is. So, what I mean to say that just by adopting these three features is not fulfilling our active vibration control part. So, then you see the other part in the active vibration control started from the material side. There are various materials known as you see the smart material, through which the sensing and actuation features can be adopted straightway. Just like you see the human body, which is one of the we can say the smart structure is there, where the sensing and the actuation straightway there in the millisecond response feature. So, based on that you see we categorize these materials under we can say the smart material or intelligent material started from the piezoelectric material, and even in that we discussed about the man-made or the naturally available materials. But man-made materials based on mainly the ceramics, even you see the PZT materials, means the piezoelectric ceramics material, or even the polymers are there, which can be acted as the piezoelectric material, through which we can sense the vibration response, and also at the same time they can be actuated the forces which are being required to suppress the vibrations. So, we discussed right from the piezoelectric accelerometers to the actuator part, and you see even whatever the profile of the surface is, even the rectangular beam is there, circular profile is there, any kind of irregular surfaces are there, these PZD patches can be straightway acted. So, that part we discussed in the beginning of the material. But sometimes you see, since these PZD patches which is starting from the lead only, because of the severity in the environmental features, even nowadays there are various other materials which are being using instead of this PZT. Then the secondly part then we move to the electrorheological fluid and the magnetorheological fluids. So, these fluids they can be act as the damper to suppress down the vibration, and also they can be act as the actuator part based on the intensity of the applied field, either the electrical or the this magnetic field, or even you see based on what the carrier fluid is there, in which you see the entire molecules, the polarized molecules are being there. We can simply add the viscosity by applying these fluxes, the magnetic flux or the electric field. And these the polarized elements, they can be symmetrically arranged in such a way that the resistance can be provided in a stronger way, and even they can produce a high amount of the actuation forces as per the requirement. We discussed about that the electrorheological fluid and this magnetorheological fluid according to their applications, where you see right from the aviation to our smart machineries, the computer numerical control machines, these ER or MR fluids are absolutely we can say adaptable. Even nowadays, even when the trains are being under the crushing action, means when the impact loadings are there, if we want to just provide a resistance in the this load transfer, this impact force transfer, this transmission, these ER fluids have an excellent applications towards that against the crashing feature of these trains. And even you see where you see with the helicopters and many other applications, these fluids are being actively applied. Then we discussed about the shape memory alloy. This is one of the excellent feature that even sometimes we are discussing about the elastic deformation, where we know that when the loading and unloading conditions are there, there is no permanent set of deformation, and the whatever the specimen size or the shape is there, there is no change in that. But the shape memory alloys are such kind of materials, they can recover their own shape when unloading is there, even they are at the inelastic or the plastic deformations. So you see here this anthropomic features along with all the mechanical properties, they have you see the excellent part with these shape memory alloy. So in the last lecture we mainly discussed about the shape memory alloys and what exactly the applications are there for vibration control. Even you see here they can be act as a straightway damper when they are just integrating themselves in the entire wire damper is there, and they can be coiled you see here as the stiffener feature. So we have both the spring energy as well as you see the damping feature towards towards suppression and means to say the absorption of the energy or the dissipation of energy, and the same time you see to control the entire oscillation by absorbing features or by we can say saving energy. They can straightway save the energy, and then they can we can say release the energy according to the requirement. So what I mean to say that these shape memory alloys can be featured out in both the way. They can be acted as the damper, they can be also acted as the actuator feature wherever it is being required. So that is why you see here many of the applications are there of the shape memory materials towards the vibration and even for various biodynamical, right from the bone to teeth to various other applications. These shape memory alloys materials have an they just showed their excellent we can say applications towards that. So in the last lecture for this material side active vibration control part, the electromagnetic dampers are there. Again you see here we are going to use the electromagnetic feature as we discussed about the ER or the electrological and magnetorogical fluid. We discussed about the electrodestructive and magnetodestructive the materials, and then the third part with the same electro and magnetic part, they can straightway be acted as the electromagnetic damper. Generally we are saying that the ED or EM part, the EM dampers. So this type of active suspension simply uses for linear electromagnetic motors, which can be attached to each of the wheels wherever you see here these the suspension is being required, where the absorption and the dissipation feature is essentially required against the shock loading. And these we can say electromagnetic devices like the motors just provides extremely fast response, because of the response time is very less in these types, and they allow to regenerate the power consumed by utilizing motor as the generator. So here one of the important feature in the electromagnetic these motors, they can absorb the energy even at the resonant feature, and whenever it is being required, these motors can be acted as the generator, through which we can again reutilize whatever the consumed we can say energy or the power is there in those devices. So this nearly surmounts the issues of the slow response times and the high power consumption of the hydraulic systems. So that's wherever we just want the immediate response and even we can say these repower utilization, then we can say this is one of the important device for such kind of applications. So for the using of this electromagnetic actuator, which I am going to show that you see in the next slide, the kinetic energy is mainly converted into the electrical energy. So whatever you see the motion or when the shock features are being coming towards the vehicle, they are simply absorbing the energy. So this energy is mainly in the form of kinetic energy, and then according to the design of this electromagnetic actuator, this entire kinetic energy is being converted into the electrical energy, which is then you see feeded to the other motors wherever it is being like required to convert back to its kinetic energy with the control actions of the dynamic systems. So that is how you see the entire these electromagnetic this motor or generator, means the devices are mainly working. First, if any excitation is being there at any of the surface where these the devices are being attached to it, they can straightway absorb the energy right from kinetic energy to electrical energy, and then wherever it is being required they can transfer this energy, and this electric energy can be re-transferred or retransmitted to the kinetic energy in terms of the generator. So by using power electronic devices in electric circuits, good mechanical characteristics of these devices can be achieved, and the characteristic can be altered by the switching of the circuit, so that you see here again the mechanical energy can be again reutilized in the power electronic devices in terms of the electric energy. So you see, this is one of the beauty of the feature of this electromagnetic action there. So as you can see, these electromagnetic actuators are there. We have this motor which like the electric energy motor is there, and because of this magnetic action, these these dynamic actions are being happening, means this is you see like the reciprocal motions are there. So when this motion is there, the entire kinetic energy which is being coming to the system, when it is being attached to any dynamic system, this can be straightway absorbed here, and then this energy is being converted into the electrical energy. So here you see this absorbed energy will be retained in form of electric energy, and then wherever it is required, this again you see with this particular part where we have you see all the like the circular motion of this this entire magnet part, it can be back to this electric energy to the mechanical energy part. So again you see here they can be act as the actuator feature through these actions. So in most of these electromagnetic dampers, certainly we just want to see that what kind of actions can be happened, because you see this is what the electromagnetic the devices are there, in which there is a clear conversion of the kinetic to electrical energy, but at the same time they are acting as the damper. So if you are talking about general damper feature, then we know that the energy is converted into heat, and the dissipation features are being there without being used. So the entire energy can be transferred in terms of the heat. And in electromagnetic dampers, the dissipated energy can be stored, and the electrical energy you see which is being the stored form can be used further wherever it is being required. So the use of these electromagnetic dampers in the suspension systems have various we can say benefits as compared to this hydraulic, pneumatic or any other mechanical dampers, because nowadays you see in this particular case the main feature is that they are acting not only as the motor or generator part, they can be just store the energy, and they can release the energy wherever it is being required. And though you see the spring can do this part, but whenever we have the huge amount of energy at the resonance feature, or even the shock loading is there, where we know that you see the impact kind of you see the loadings are there, and sudden amount of huge energies are being coming to the system, these electromagnetic dampers can be straightway act in such a way that whatever the energy which is coming in terms of the kinetic energy can be straightway absorbed and convert into the electric energy, and they can restore the energy for the highest time, and with the quick response they can immediately release the energy in terms of the kinetic part. So this is one of the beauty part in this. So we can say that the electromagnetic dampers can function simultaneously as the sensor and the actuator. So the spring effect can be added to the system by means of the electromagnets, which are being powered by the permanent magnets. So here you see here, when we just want to sense the things, means whatever the sensing features are there, then this electromagnetic dampers can be act as you see with the inclusion of these permanent magnets, the spring features. So this is what you see here, whatever the things are being coming in terms of, that is what I told you, that if you want to store the energy, then they are simply acting as the spring part, even whatever the highest energies are there, and when they are just saving the energy, or we are saying that when they are storing the energy, this energy is being absorbed with the simultaneous action of these the permanent magnets, and you see here this kinetic energy is being converted into the electrical features. Moreover, these electromagnetic dampers can work under very low static frictions. So, you see here it is not that all the time you see here we need to know you see that highest amount of energies are being there and then can be used there. So, here the main thing is the damping coefficient is being controlled rapidly and reliably through the electrical manipulators. So, you see here these the manipulators which can allow them to even work at whatever the damping coefficients are there under the low static frictions. So, using electromagnetic dampers which are being composed of these electromechanical elements, the kinetic energy of the entire vehicle body vibration can be regenerated as the useful electrical energy, and then this electrical energy can be stored and then it can be reutilized even in terms of the kinetic energy as well in the actuator feature. So, electromagnetic dampers, for which we are saying that when they are acting as the actuators, they have the potential to be used in the active suspension system effectively and efficiently. They can actuate with the quick response time, as we are just setting that what exactly the response time is being required to the system. So, automobiles and the trucks, they have the shock absorber to damp out the vibration experienced due to roughness of the roads. That is what I told you. Wherever you see either that we have any irregular surface properties are there, or when we have the bump kind of features, and when these vehicles are just traveling across that, whatever the shock or the the sudden these impact energies are being coming, or the impulsive forces are being acted towards the real system, these electromagnetic dampers are able to suppress the energy, to store the energy, to absorb the energy, and you see here they can we can say that they can be reutilize this kinetic energy into we can say the electric energy to the kinetic energy in that. However, the energy in conventional shock absorber gets dissipated as heat and cannot be used back in any way. That is what you see the shock absorber, which we discussed in one of our passive vibration control, in which you see we have the clear arrangement of the dashpot, in which you see the viscous dampings are there, and over which we have the spring parts are there. So, spring can store the energy and transmitted this stored energy in the dashpot, and this dashpot is dissipation features are being occurred, some of the energy is being absorbed. So, this is not an excellent feature in which you see the proper conversion energy right from we can say kinetic energy to strain energy, and strain energy to kinetic energy can be done in the normal shock absorber. But here whatever the kinetic energy is being coming to the system, it can be regenerated right from the kinetic energy to electric energy, and then electric energy to kinetic energy. So, the regenerative feature of the electromagnetic shock absorber provide the means for recovering the energy dissipated in the shock absorbers, and that is one of the unique feature in which we can simply isolate the system and we can reutilize the entire energy part. So, electromagnetic shock absorber for potential we can say because of these special features, they can be used in the vehicles along with the we can say the dynamic systems are there, means wherever we know that the dynamic actions have been predominating. So, they can be attached or they can be fabricated and tested for their performance straightway, that you see whether they can be sustained the huge amount of vibration under the loading condition, and you see the irregular surfaces are being there at higher speed, lower speed, means whatever even the high amplitude or low amplitude of the oscillation is there, or even the exciting frequencies of the low to high frequencies, these electromagnetic dampers can be effectively used at whatever the energy levels are. So, electromagnetic damper consists of the two main parts as we discussed. One, the fixed stator is there, in which we need to have a permanent kind of the magnets, and second is the movable slider. So, in this part especially when when we are looking towards that, the first thing is there that when these when the magnetic movements are there, all these the magnetic lines are being circulated all around the iron yoke. And then you see here, because of the intensity of this, the entire feature is being we can say whatever the movable slider and the like the stator parts are there, these magnetic lines can be generated, and the damper plate which is you see on top of that, you can see that this is what my damper plates are. They can be straightway absorb the things, they can absorb you see whatever the kind of excitations are coming in that. So when we are looking the two main parts, you can see that we have clear two parts here, the electromagnetic damper. First, the annulary shaped magnets supported by the non-magnetic rod. So you see that you see like the non-magnetic rods are being supported by this. So we have you see these all the coils are there, and you can see that this is what my spacer, and in that this especially this part which is you see like the solid part is my magnets. And with this stator part which is being outside, you see here they are straightway being supported by this non-magnetic rod. So like with these kind of things, whenever you see the magnet which is being fastened together with the non-magnetic tube, then you see whatever the stator points are there, means we can say that when the fixed point and the movable points are there, then straightway you see these magnetic fields can be generated. So we have you see this is what you see the movable part which is absolutely inside the magnet. This red part which is clear, you see the coupled part from this mover is my magnets are there, and this is what my spacer, the dark part in which this is my spacer. We have the coils all around, and you see the stator part is there which is just providing the outer casing features there itself. So when you see the stator and these magnets, when they make you see the outer casing, the movable part, when they are just moving together, you see here under these magnetic fields, they can be straightway you see. So we have both the things. We have you see the stator, which is you see, if you look at that at the outer part, you see this is my stator, just stator you see. After that we have the coiled part. So these coils you see here which are being supporting our spacer, and you see the magnet part you see here which is straightway you see coupled with the mover part. We can say that we can straightway provide the electromagnetic field towards you see the part, and whenever you see the kinetic energy through the movement of this part, the mover part is coming to the system, they can be straightway absorbed with the using of these magnet feature. So the stator you see, when we are talking about that, they are simply the windings in which what we have potentially position of this stator, especially the windings, and they can be act as even the temperature sensors together. So these windings are simply integrated into the metal cylinder, which is what you see the cylindrical features are there in the stator. And the mover, which we are saying that the slider, can be utilized in between you see the permanent magnets that are screwed to the aluminum rod via this spacer, which we are saying that the pole pieces just outside the red spots which I was showing there. So when these like the mover, or we can say the slider, which are being there, which we are utilizing specially under the like the permanent magnets, the whatever the movement through these excitations, when they are just coming to the system, the kinetic energy is being there, and this kinetic energy is being now stored because of these all the windings are being there all around these mover part. So they can be stored this entire kinetic energy. They convert first into the electric energy because of the environmental features in all you see the magnetic environment, and then you see here this energy can be regenerated again back to the mechanical. So the regenerative damper converts the vibration of the body mass into the useful, we can say, electric energy. Compensating of high energy consumption is basically like one of the special application of the active suspension. So this is one of the feature you see here which is being happening there, the mechanism in which you see here the entire stator windings which is being there together, you see here when the movements are being there with our, we can say whatever the permanent magnets are there, they can be converted this kinetic energy into electric energy, and then it can be way back to the system again in forms of the kinetic features. So when we are talking about the electromagnetic damper, the damper is also, we can say that, just robust in the design, because it consisting the permanent magnets which in the combination with the electromagnets as the major component, and you see here this is a uniform, we can say, structure in which not much you see the complexities are there in the connection of these movable and the stator parts. So, this is somewhat the cost effective feature, and we can say that the regenerative electromagnetic damper is absolutely, we can say that either we can go with the tubular, we can go with the linear or the brushless DC motor, and that can be used straight away in, you see, like the active suspension system. So, whenever we see that there is a clear vibration part, even we can straight away use these as the passive or even the semi active devices. So, like the ED part is really means the electromagnetic damper is an effective like utilization of the energy wherever it is being required. So, when we are talking about the passive or semi active modes of the vibration control, this electromagnetic damper operates as the generator, which is like converting the vibration of the entire vehicle body in terms of the continuous or the shocking to electrical energy, and the motional electromagnetic forces EMF, which we are saying that EMF basically is induced to the coil due to relative motion of the mover in the stator part. And this generated electromotive force even creates an opposing force that is proportional to the velocity of mover within the system, and this causing the viscous damping effect within the entire system. So, it is a clear resistant features are being there because of the motion of this mover part within the electromagnetic field. So, we can say that this is what some kind of, we can say, the passive features of that. On the other hand, in the active mode, the coils are energized so that the electromagnetic damper can operate as an actuator part. So, instead of, you see, like the dissipating or absorbing the energy, now we are transferring the energy back to the system, and this can be this can be even reacted as the actuator part in the system. So, this is what you see, like the working functions are, that when you see, like when the vehicle body which is being generating, you see the kinetic energy and which is being converted into the electric energy, these the EMF forces which are being generated in the coils due to relative motion of this movement of the motion or the, we can say, the stator is like creating the opposing force there, and this opposing force in the active vibration control can be straightway like used as the actuator force back to the system to suppress the vibration. While if you are using this as this the passive controller, this like force, when it is being moving with the velocity, whatever the velocity is there, is simply causing the damping part, and with the damping you see here they can be straightway like dissipated the energy. So, that is why you see here in the passive or semi active we cannot reutilize as the actuator feature in that, but it is absolutely depending on the design features there. So, electromagnetic damper is designed like we can say it is just like designed on the basis of what the optimum topology features are there, means the selection, the location part, what exactly the environmental features are there, and continues with the prototype ED design procedure to achieve the maximum thrust force density part there itself, and then can be utilized, you see here the various we can say like the application based on what exactly the magnetic circuit principles are there along with the stator and moving features. So, once you have the prototype ED, you can basically experiment those things, and then you can get that how we can like accurately redesign or how much electromagnetic forces are to be generated through like the sensing feature, whatever the things are being coming in terms of energy, and how much force can be reacted towards the body itself. So, this is one of, you see, the perfect ED design. So, now we are going to show you see like one more example in that, but previously when we show that, you see the two main options with respect to, you see like whatever the features are there, one which was depicts annulary shaped magnets which were being supported by the non ferromagnetic rod, and the second was showing, you see like with the magnet fastened together with the non magnetic tube, in which you see the sliding like motions are being there in the tube shielding to the stator coiled. So, these two you see like the different types are there based on their manufacturing limitation and the issues, we can go with that, and based on what like the kind of forces which are being generated back to the system for suppression of vibration, these designs are to be there, whether we are going with the annulary shape, or whether you see we are going with this, you know, like when we are simply shielding the entire, you see, you know, like the stator coils to the non-magnetic tube. So what exactly the things are being required that can be done. So the configuration which limits the minimum size of these whatever, you know, like the effective air gap to the sum of those two tubes, that can be, you see, easily we can say manufactured, and that can, you know, like we can say save the weight and the volume in that case where you see, you know, like the additional this liner guides are being required for supporting the entire annular feature. So we can say that the configuration in which you see, you know, like the fastened features are being there with these two parts, means these two tubes absolutely, in which you see, you know, like the minimum air gaps are there. It's very easy to manufacture, and also you see here it has very less weight because we don't have any liner guides towards that. So magnetic circuit, which is also, you see, one of the basic requirement, we need to just improve the damping performance by putting this, you know, like the less volume towards that, so that you see here there is not many losses are there because of the gap itself. So when we are talking about the design parameters, we need to consider the dimension of the magnets and the coils, and then we can show this especially towards the lumped model, because ultimately you see we need to use this as the damper feature. So we can simply show on the lumped model of the proposed electromagnetic shock absorber and what is the equivalent magnetic circuit is being required. But one of the key issue in designing of such ED dampers are the direction of flux density must be, you know, like in the accordance, where you see here we just need the effective utilization or effective, you see, you know, like the intensity of this the utilization of the intensity of this magnetic field together. So as you can see here, we have, you see, like the three main things. One, outside you see we have the stator core. So this is, you see, you know, like outside the stator cores are there together, and when we are trying to make this, you see these discrete model, where you see, you know, like we can say this linear dump models are there. So lumped model is clearly showing that, you see, this is what my resistance is. So this is, you see, the first the gap feature is there, R gap, this is my R, the resistance of the pole part is there, this is my resistant magnet is there, and this is resistance core is there. So in the coil particular, you can see that the coil is in such a way that it arranged with the gap of G, and the total, you see, you know, like in this permanent magnet motor part you see here, or we can say the equivalent magnetic circuit which was shown by the Babak Ibrahim in 1999. It is clear that you see here these permanent magnets are being there, and in between that you see here the entire feature, whatever you see, you know, like we can say the electromagnetic force, the EMF forces are generated, and they are straight, you see, you know, like acting towards that. So we have the coil, we have, you see, you know, like the pole places together. So these pole places which is clearly showing, you see, the white part, in that you see here we have clear resistant feature in this. So when we are talking about a magnetic circuit which is closed in like which is closed path of the magnetic flux, and they are, you know, like containing the ferromagnetic material and the field source in such a way that the permanent magnet and the coils can be effectively utilized in terms of their force generations. So for one pole pair, the iron core has an infinite magnetic permeability without having any leakage of the flux that can be, you know, like just adjust with the connecting rod. So its saturation, or we can say its reactance, can be immediately neglected. So when we are talking about this circuit, we can say that there are, you know, like various segments, say M segments are there with the different permeability. Then we can say the flux which is being generated phi into the magnetic field phi h into dt is equals to the entire summation of, or the entire M segment summation of hi Li equals to n into I, where resistance Ri is nothing but equals to Li by mu I Ai. This is, you see, you know, like the, we can say the reluctance of the ith element, and we can say that whatever the cross sectional area is there, this reluctance is absolutely depending on this area part. And when we are talking about, you see, the magnetic flux which is the phi in any of the element, we can say that the total of magnetic field which is, you know, like somewhat we can say varying parameter with individual segment. So phi into h is nothing but the magnetic flux into whatever you see the magnetic field which is being available there, is just with the delta time t. This just simply showing that whatever the forces are being there, it is equals to n into I. And also you see here, when we are talking about individual section, we have you see the reluctance Ri at the ith element into whatever you see like the magnetic flux in the ith element. The multiplication is clearly giving that how the variations are being there along with m of k, where m we know that the total segments are there and it is nothing but the total force m of k. When we are just going with the entire n part, the total force is being there, which is nothing but the magnetomotive force, mmf force is there. So when we are talking about you see of any source, when the total sources are there, we can just take the total amount of like the sources and we can simply show that how much you see the magnetomotive forces are being generated along with the reluctance and the magnetic flux of these like the entire elements are there. So you see here, when we are saying that you see like these two equations which are clearly showing you see the balance features for the individual section to the entire part, we can say that these lumped model is just showing the linear propagation of these forces when they are being like attached in the series way. So here we have you see like the m, which is nothing but equals to the Ni. N is nothing but the total number of coils, how many turns are there in the coils, and m which we are showing here as the source part, particular in the forcing feature m of k, which we are saying like nothing but the magnetomotive force is nothing but equals to HcLm for a individual magnet, where Lm is nothing but the total this we can say the length of the magnet, and Hc is nothing but the correctivity in the field part. So when we are using this like the equation, then again we can rebalance this equation with the corrective magnetic field intensity. So we are saying that the R magnet plus 2 times of the R gap into phi z, and phi z is nothing but the air gap magnetic flux, because we know that this is one of the important tasks you see in that how much you see the air gap is there through which you see the magnetic flux is being generated. So R magnet plus 2 times of R gap, when it is being multiplied with this whatever the flux magnetic flux air gap R phi gap is equals to the Hc tau m, and we know that Hc is nothing but the corrective magnetic field intensity, the intensity is there, which can be even multiplied with whatever you see like the stresses which are being there because of these force action of the magnet. Or else we can also equate to the Brem divided by mu record into tau m, and this Brem is nothing but equals to the remagnet flux density, because we need to just see that how much you see like the magnetic effect is being there in that. So remagnet flux density, and we know that the mu Rem is the permeability in the recoiling of the magnets. So it is what you see here, the clear conversion when you see the electromagnetic forces or the electric energy is repassing to that, and it is absolutely sensitive to that how much air gap is being there in between this magnetic flux. So mu Rem by mu Rec into tau m is clearly like we can say deciding that how much you see the phi z is being required in that. So we can get to see the reluctance in the magnet and the gap part. So when we are talking about the magnetic reluctance R magnet, which we shown previously, it is nothing but equals to tau m divided by mu Rec pi into Lm plus s square minus s square, or even we can get the reluctance of the gap. So gap reluctance is nothing but equals to its G, that how much distance is there in the G. If you look at the diagram, this is what my G is there. So this G can be clearly like relate with this Lm, which is nothing but the length of the magnet, and this gap is there as we can say Sc, or it is the total S is there. So when we are just talking about you see the distances, this tau m and tau s and this Sc, we can straightway relate these things together. You see here like finding out that how much you see like the gap reluctance, or how much you see like the regenerative reluctances are there in that. So when we are just talking about the remagnet, or when we are talking about the gap reluctance, then it is straight where you see the magnet reluctance is nothing but equals to tau m, which was you see the distance divided by this, and the G was vertical distance in divided by mu 0 pi square Lm plus s plus G by 2 into tau minus tau m is what is the total difference between tau and tau m is there divided by 2. So, air gap magnetic flux density, which is the one of the important feature is there, can also be get, you see, Bz is equals to Brem tau m mu 0 Hc divided by 2Z Brem plus mu m tau 0 mu 0 tau m mu 0 Hc Ag by Am. So, here it is, you see, the cross sectional area where you see the magnet and these G features are there, and the ratio is clearly giving that how much, you see, like the magnet the air gap magnetic flux are being there in that. And if you want to calculate now the electromotion forces, you see, like the EMF forces are there for any phase. Say if you are talking about the ith phase, then certainly you see it is absolutely depending on that what the flux linkages are there in between, you see, the magnets. So, when we are talking about this lambda Pm, it is nothing but equals to the linkage feature in between the permanent magnets in the phase part. So, we can say this EMF part E is nothing but equals to d lambda Pm divided by dt, or else even we can further go with the Z part. So, it is d lambda m by dz into dz by dt, where we can say that the lambda Pm, which is something, you see, like we can say the flux linkage in the phase due to the magnets, is nothing but equals to the number of coils, the n into phi z cos pi divided by tau into z, and tau is the time constant, you see, the tau is like the distance in between, like these horizontal distances are there in between, like these coils and other features. We can get, you see, here the EMF forces at the ith element is nothing but equals to d lambda Pm divided by dt, or else even we can say that when we are just differentiating out this lambda Pm, which we shown in the previous part, this which is nothing but equals to minus n phi z pi by tau sin pi by tau z dz by dt. So, this is, you see, here the electromagnetic these forces are being generated when you see there is a conversion of the kinetic energy into the electric energy, the movement features are being there. So, even we can simply show the damping coefficient, which is one of the specific property of the electromagnetic dampers with the this Lm by ds ratio. So, this is, you see, like we can say the dm by ls ratio is nothing but the normalized magnet length with different values of the ds. So, we can see that when they are changing the d value, means when it is in the reducing part, you see, right from, like when it is the bluish feature, and when it is just going down to this, like the pink part, it is, like the d value is down, and there is a clear part is there as the Lm by ds ratio is, like increasing. The damping coefficient is linearly increasing up to point, you see, Lm by ds up 0.5, and when it is going beyond, you see, like 0.5, then there is a parabolic we can say expansions are there, but this expansion is quite rapid when the d value is high. That means, you see, here when you know that the normalized magnet length for various ds value means the damping value is being high, then certainly you see here the variation for certain length is linear, and then there is, like the nonlinear features are being there together. We can even show the commercially that how these like the EDs are simply looking towards that. So, we have, you see, the stator. If you look at these are the stator part and the mover part, in which you see the pole and the magnets are being coupled together, they are being there within that, and through these permanent magnets these fields are generated and they can be acted effectively in terms of, we can say, the damping devices. So, this is something, you see, here which is, like nowadays very much in use, especially towards the shock loading, the electromagnetic dampers, and even for, like the sophisticated control with the quick responses in terms of the sensing to actuation, these are effectively being used especially against the shock loading part. So, in this lecture, you see here we discussed about the main mechanism, we discussed about that what exactly the relations are there with the air gap in the magnetic flux, right from, you see, the magnet to the air gap to all the dimensional features. When we are taking these electromagnetic dampers as the lump parameter, we can simply configure in the proper circuit and we can define the gaps, and then we can see that how much effectively we can generate the magnetic flux, or how we can simply, like consume the kinetic energy in terms of the electrical energy, and how much, you see, the electromagnetic forces are being generated when we just require this as the actuator force. So, this is all about this lecture. In the next lecture now, we are going to discuss about, which is the last part, not basically from the material aspect of the active vibration control or the passive vibration control, but this is the last part in this module, in which we are going to discuss about the various numerical problems which are being associated with the real machinery, how we can resolve those issues, what exactly the parametric features are there which we can simply like measure, and we can calculate rather, and we can effectively like apply to the real features of the machine under the exciting forces. Thank you.